we can find the pH using only the first K value. And if we can't, you really have a mess of algebra. Okay, so we really hope that we can. So let's look at an example. What are the values of H plus and A2 minus at equilibrium in 0.1 molar generic acid H2A when Ka1 is 1 times 10 to the negative 5th and Ka2 is 1 times 10 to the negative 9th? Well, we look at this and we say, okay, my two equilibria, I have H2A in equilibrium with H plus HA minus, and I have HA minus in equilibrium with H plus A2 minus. My Ka1 is equal to H plus times HA minus divided by H2A. And my Ka2 is H plus times A2 minus divided by the concentration of HA minus. Now, we can solve this by setting up a concentration table with 2 rows of change. Personally, I think it's easier to use 2 tables. I just find it less confusing. So let's set up our first one. H2A is in equilibrium with H plus HA minus. Now, this is same old that we've been doing over and over since chapter 14. We set up our ice chart. My starting concentration of the acid H2A is 0.1 molar. Hydrogen is 0, HA is 0. Minus X plus X plus X. At equilibrium, 0.1 minus X, X, and X. Okay, there's our first one. Now let's look at the second ionization. HA minus gives us H plus A2 minus. Now, here's where things get a little different and you have to think your way through. We set up our ice chart. What is my starting concentration of HA minus when it's only been produced from the first equilibrium? X. Okay, it's not 0.1 molar. Now I have a variable in here. I start at X. What's my starting concentration of hydrogen ion? X, because I made X hydrogen ion in equilibrium from the first equilibrium. What's my concentration of A2 minus? 0. So now this is going to change. How much does it change? We don't know. Does it change the same as X? Probably not. So we need a new variable. Minus Y. Okay? What's happening here? Plus Y and plus Y. So at equilibrium, for my second equilibrium, I have X minus Y, X plus Y, and Y. So now when you start to look at this to solve, it turns into a mess, which we don't want to deal with. So we see, can I make some simplifications here? The answer is yes. Most of the time we can. So if we look at the Ka values, Ka1 is 1 times 10 to the negative 5th. Is that small enough that we can say X is small compared to my starting concentration? So my H2A concentration is about 0.1, and then I have X and X. And these are my equilibrium concentrations for my first equilibrium. Now let's look at my second equilibrium. Ka2 is equal to 1 times 10 to the negative 9th. Is that quite small compared to Ka1? So what that means is that Y is small compared to X. So X minus Y is about equal to X. X plus Y is about equal to X, and this is Y. So at the end of my second equilibrium, the concentration of the hydrogen ion is about equal to X. So I got X from the first ionization, so I can find pH from the first ionization. So most of the time, you don't even have to think about the second one. However, this question said, what are the concentrations of the hydrogen ion and the A2 minus? So we do have to deal with both of them. So let's do the hydrogen ion first. I know that Ka1 is equal to 1.0 times 10 to the negative fifth. So that's equal to my hydrogen concentration times my HA minus concentration divided by my H2A concentration. So 1 times 10 to the negative fifth is equal to X times X divided by 0.1. Multiplying across now. 1.0 times 10 to the negative sixth, I get that by multiplying here, is equal to X squared. So X is equal to the square root of 1 times 10 to the negative sixth, 1 times 10 to the negative third molar. Now, what is X representing for us? That is representing the hydrogen ion concentration. So we've just solved the first part of our question. We have the hydrogen concentration. And from that, we can find the pH. Now let's look at the second ionization. Ka2 is equal to the hydrogen concentration times the A2 minus concentration divided by the HA minus concentration. So Ka2, 1.0 times 10 to the negative ninth is equal to the hydrogen concentration X times the A2 concentration Y divided by the HA concentration X. Now look at that algebraically and tell me what happens here. You cancel out the X's. So Ka2, 1 times 10 to the negative ninth, is equal to Y. So I don't even have to do any multiplying and dividing. So this is always true, and I know you love to hear the words never and always so you can memorize them. This is one of the few times that we have an always. When Ka2 is small compared to Ka1, the concentration of the minus 2 anion will be equal to Ka2. So if this was on a test, you wouldn't have to do anything except write this. Ka2 is equal to A2 minus. Okay, and you just write the number down if it asks you to calculate that. So we find the proton concentration from the first ionization. The only thing we're using the second ionization for most times is to figure out the A2 minus. So let's have you do this last one, and just go ahead and do this individually at your seats.